I would like to continue our discussion of light and Planck's equation. Now, in the last video, you learned about the photoelectric effect, in which electrons were ejected from the surface of a metal by incident light. You also learned that the number of emitted electrons and their kinetic energies could be determined as a function of light intensity and light frequency. I also exposed you to Planck's equation, which states that the energy in a photon or a quantum is equal to Planck's constant multiplied by frequency. We also talked about the fact that the speed of light is equal to the wavelength multiplied by the frequency, and that if you were to rearrange one of these equations in terms of the other, you could have a mathematical relationship between energy, speed of light, wavelength, frequency, and Planck's constant. In this equation, E is the amount of energy in a quantum or a photon. So let's do an example problem here. Light with a wavelength of 525 nanometers is green. Now remember, there are 1 billion nanometers in 1 meter. Calculate the energy for a green light photon. So the amount of energy in 1 photon. So that is a quantum of energy. Now, I would also recommend you get out your electromagnetic spectrum for this video because I will be referencing it throughout. Let's think about what we have here and what we can use to solve this problem. So we have the wavelength and we're asked about the energy. So this is a very straightforward application of Planck's equation, in which we look at the energy of a photon being equal to the Planck's constant multiplied by the speed of light, and that quantity divided by the wavelength. Now, in this case, again, wavelength is given to you in nanometers, so you needed to convert nanometers into meters, as you've seen done here. So go ahead and get out your calculator and see if you get 3.78 times 10 to the negative 19th joules. That's with 3 significant figures. I would also encourage you, as we go through these examples, to look on the electromagnetic spectrum and locate these various wavelengths and frequencies to make a connection between the amount of energy in the wave. In example 2, you're told that green light has a wavelength of approximately 5.0 times 10 to the second nanometers. And you're asked, what is the frequency of this light? So with that information, you have wavelength and you're simply asked about the frequency. So this is another straightforward application of Planck's equation, in which you are able to solve for frequency, which, remember, is denoted with the Greek symbol nu. It looks like a V. And you're able to put in the speed of light and divide that by the wavelength. Don't forget to convert the wavelength into meters, and also pay attention to your units where meters cancel out here, and you're left with the inverse of a second. And recall that those units are all the same and are the derived unit for frequency, or hertz. So grab your calculator and see if you get 6.0 times 10 to the 14th hertz. Now, in part B of this question, you are asked about the energy in joules of 1 mole of photons. Oh my goodness! Lorenzo, Romano, Amadeo, Carlo, Avogadro, because you're being asked about a chemical unit, a photon of green light. So to start off with, you're just going to use Planck's equation and use the frequency that you calculated in part A. Once you put in those variables, you're able to simply calculate this out, and you should get 4.0 times 10 to the negative 19th joules. A very small amount of energy, but we're talking about a quantum of energy called a photon. So in one photon, there's that much energy. So now we get to continue on with our computation by converting this into the energy that a mole of photons of green light would have. So, beginning your dimensional analysis here, start with what you calculated. So you know that there are 4.0 times 10 to the 19th joules in one photon. And you know there's Avogadro's number of photons in one mole. And what units does that leave you with? Joules per mole. And what are you asked? You're asked for joules in a mole. So grab your calculator and see if you get this number here with 2 sig figs, reported as 2.4 times 10 to the 5th joules in 1 mole of green light. In the last example, you're asked to find the frequency of a photon whose energy would be sufficient enough to cleave or break the bond in a chloride molecule, to break the chlorine bond. And you're also told that the chlorine bond strength is 242 kilojoules per mole. So that is the minimum threshold of energy that is needed to cleave that bond. So, where would you start? I recommend with the only information you were given. Think about it. 242 kilojoules, a measurement of energy per mole. If you consider that the energy of a photon is equal to Planck's constant multiplied by the frequency, then you can rearrange that in terms of frequency. And that is what you can use to determine the frequency by plugging in the energy you were given, and you already know Planck's constant. You just need to make sure that you are converting kilojoules into joules so that you are using the correct units. All right, so kilojoules, in 1 kilojoule there are 1,000 joules. Joules will then cancel with joules multiplied by seconds in the denominator here. Then you're going to be left with, in 1 mole, will cancel with the inverse of a mole, which is going to leave you with the following units. All right, you're going to be left with the inverse over photons. So what does that even mean? Well, remember you're being asked what is the frequency. So the inverse of a second makes sense. That's hertz. Remember you're also being asked the frequency of a photon, of 1 photon. So in 1 photon, you should get 6.06 times 10 to the 14th hertz. So that is the amount of energy per 1 photon that is necessary to break this chloride bond. Looking at your electromagnetic spectrum, you can see that this frequency of light here falls within this range of the spectrum. And as I asked you to do earlier in the video, have this out. I would always encourage you to look at it and think about wavelength, frequency, and the amount of energy. So in this video, we've continued our discussion of light and atomic theory. You do have a problem set that I want you to work on, And I'll see you guys in class.